Hi everyone. Today we're going to be going through our last video for related rates problems. We're going to be talking about cone and lamppost problems. So after today you'll have a day to practice just the cone and lamppost types, and then beyond that you'll be getting a lot of practice where these types will be all mixed together. So let's go ahead and start with a couple of cone problems. And you're going to see kind of why these are day 3. There's a little bit extra going on here that we need to pay attention to. The good news is that once you learn the trick, it's going to work for all of these types of problems. So here's our setup. We have a conical cup, so it's just a cone shape, and we know it's 4 centimeters across and 6 centimeters deep. So what we're looking at is our cone. 4 centimeters all the way across, so we're talking about the diameter there of the base, and then it's 6 centimeters deep. Obviously my picture is not to scale. Okay, so we know water is leaking out of the bottom at the rate of 2 cubic centimeters per second. We want to know how fast the water level is dropping when the height of the water is 3 centimeters. So here we go. That water leaking out, that's telling us the rate of change of the volume. So I know I have to relate my volume here. I have to come up with an equation for the volume of a cone. So here's what I'm going to do. I know it's 4 centimeters across and 6 centimeters deep. But at any given point in time, so let's just say our water level was here, I know that this is my radius and this is my height. So if I had it that full of water. We don't know what that radius and height is. We just know the radius and height at the top. So if I'm talking about volume, I know the volume of a cone is pi over 3 r squared h. And so what I notice right away is that I have a little bit of an issue, because if I have this equation, I have the variable r and h. So if I differentiate it, I'm going to get a product rule, and I'm going to need to know some information about r and h. If I look back at my problem, though, it looks like it's only giving me information about h. So I have to come up with a way to get volume just in terms of h. So here's what we're going to do. We're going to use this information right here to set up a proportion. So I know the ratio of the radius to the height is just equal to the ratio of this radius to this height. Now we have to be careful. If it's 4 centimeters across, I know the radius is going to be 2 centimeters. So r over h is equal to 2 over 6, or 1/3. Now, if I want to express my volume in terms of h, I need to solve this for r in terms of h. So I'm going to go ahead and cross multiply, so I get 3r is equal to h. And then by dividing, I know r is equal to h over 3. So I'm going to use that now to substitute in my original equation. So I have volume just in terms of h. So now I have pi over 3. My r, I just said, was h over 3, and that's squared times h. So if we simplify that, 3 squared is 9 times 3. I'm going to have pi over 27. Then h squared times h is going to give me h cubed. So there's my volume just in terms of h. And now this is exactly like all the other related rates problems that we've done. So we're going to differentiate with respect to time. dv dt, if I multiply by 3, I get 3 over 27, which is the same as 1 over 9. So pi over 9, h squared, dh dt. So now I need an h, I need dh dt, and I've got this missing dv dt. So let's see what we know. At the top, it told us that the water is leaking out of the bottom at a rate of 2 cubic centimeters per second. So that tells me my volume is decreasing. So I'm going to have a negative 2 cubic centimeters per second. We want to know how fast the water level is dropping. So that's the rate of change of h with respect to t. And we want to know when that happens when the water is 3 centimeters. So when h is 3. So now we can just plug in and solve. So dv dt we said is negative 2 equals pi over 9. My h is 3 squared dH dt. The nice thing here is my 3 squared and my 9 in the denominator here cancels. So if I divide by pi, I get dH dt equals -2 over pi centimeters per second. Which makes sense. If this cup, the water is essentially draining out, I would expect that that water level is dropping. Since we have a negative rate of change here, it indicates that that water level is decreasing. So let's go ahead and do one more. Another cone problem here. Okay, so now we have a funnel in the shape of an inverted cone, is 30 centimeters deep and has a diameter of 20 centimeters. So this diameter is 20, and our height of that cone is 30. Okay, liquid is flowing out of the funnel at the rate of 12 cubic centimeters per second, and we want to know again what rate is the height of the liquid decreasing when the liquid is 20 centimeters deep. So again, I'm going to draw in at any given point in time. I have a radius r and a height h. I know my volume is pi over 3 r squared h. And again, I'm trying to find out information about height, so I want my volume just in terms of h. So I'm going to set up my proportion. I have r over h is, in this case, we have to be careful. They gave us a diameter, so our radius is 10. Our height is 30. So again, we have 1 over 3. I'm going to cross multiply. I get 3r is equal to h, or r is equal to h over 3. So now I'm going to go ahead and substitute in, just like we did up top, pi over 3 times r over 3 squared times h. And so if we simplify, we get pi over 27. Oops, I'm sorry, this should have been an h. Let's make that an h. Pi over 27 h cubed. So again, now we have a formula just in terms of h, so we're going to go ahead and do our normal steps. We're going to differentiate with respect to t. So that'll give us pi over 9 h squared dH dt. So we need to figure out h, dH dt, and our dV dt. So let's see, we were told that liquid was flowing out of the funnel at a rate of 12 cubic centimeters per second. So we have a negative rate of change for our volume. We want to know the rate at which the height is changing at the instance when the liquid in the funnel is 20 centimeters deep, so when h is 20. So let's go plug everything in. -12 is equal to pi over 9 times 20 squared times dH dt. So I get -12 equals, let's see, 400 pi over 9 times dH dt. So to isolate dH dt, I'm going to take -12 times 9 over 400 pi. And let's see what we get. I get -108 over 400 pi. Let's see if we can reduce that. It's going to come down to -27 over 100 pi, and our units are going to be centimeters per second. So that's the rate of the change of the height. And again, because that liquid is flowing out of the funnel, we would expect that water level to be decreasing, and since this is negative, that matches. So those are our funnel problems, or our cone problems, excuse me. So to wrap it up here, now we're going to look at our lamp post problems. And we're going to be using this idea of proportionality or similarity again in these problems. So here we go. I have a person 2 meters tall is walking towards a lamppost on level ground at a rate of 0.5 meters per second. The lamp on the post is 5 meters high, and I want to know how fast the length of the person's shadow is decreasing when that person is 3 meters from the post. And then we're going to talk about at what rate is the tip of his shadow moving. So let's go ahead and draw this out. So here I've got my lamppost here. I know that this is 5 meters high. And then I know I've got my person here. And that person is 2 meters tall. Okay, and I know this person is walking towards the lamppost. So I'm just going to draw that to indicate his direction. So I'm going to call this X and this Y. Now, the first question I need to answer is, let's see, how fast is the length of the person's shadow decreasing? So if this is my lamppost, so I'm just going to, here's my light coming out of my lamppost. I know that this right here is going to represent that person's shadow. So when I'm looking for the rate at which the length of the person's shadow is decreasing, I'm trying to find dx dt. So if I look at this, I'm going to use my right triangle similarity to set up a proportion. So I know that x over 2 is equal to x plus y over 5. So now, before I differentiate, I'm going to do a little bit of simplification. So I'm going to cross multiply. I'm going to get 5x equals 2 times x plus y. 5x equals 2x plus 2y. And then if I collect all of my x terms on this side, I get 3x equals 2y. So now I've got a nice, simple equation that relates these variables together. So now I'm going to differentiate. So the derivative of 3x is just 3 dx dt. And on the right side, I'm going to get 2 times dy dt. So all I need to be able to solve is I have dx dt, and I need dy dt here. So let's see which one we know. So the problem told us that the person was walking towards a lamppost on level ground at a rate of 0.5 meters per second. So this shows me the direction that I'm walking. So I know dy dt is 0.5 meters per second, but I need to be very careful with my sign here. Since I'm walking towards the lamppost, that distance is decreasing, so I have a negative rate of change here. Now, if I want to know how fast the length of the person's shadow is decreasing, that's my dx dt. And so you'll notice with these problems, that rate actually isn't dependent on how far they are from the post. That's some extra information. So now I can just plug in. I have 3 dx dt equals 2 times a negative 0.5. So now I have 3 dx dt equals negative 1, or dx dt equals negative 1 meter per second. So that tells me the length of his shadow is decreasing at a rate of what am I doing? I have to divide by 3. Negative 1/3 meters per second. Now, the second question is a little different. It says, at what rate is the tip of his shadow moving? So at what rate is this point moving here? So I'm going to call this whole distance z. And so this is going to be kind of part B. So I'm going to draw a little line here. I know to relate x, y, and z, I know that x plus y is going to be equal to z. So the length between me and the post plus the length of my shadow is equal to z. So now I'm going to differentiate. Well, the derivative of x with respect to t is just dx dt plus I have dy dt is equal to dz dt. Now, I just solved for dx dt. I know that's negative 1/3. dy dt I know is a negative 1/2. And so adding those together is going to give me the rate at which the tip of his shadow is moving. So dz dt equals, let's make this a common denominator, so I have negative 2/6 plus negative 3/6, so negative 5/6 meters per second. So I actually used the first part of that problem to help me really easily solve the second piece. All right, so let's do another one. And then that you'll have everything you need for this related rates piece. Okay, so now we have a man 6 feet tall walking at a rate of 5 feet towards a street light that is 16 feet above the ground. So here we go. My street light here is 16 feet. I have my man here is 5. So I know this is x and this is y. Again, this is the length of his shadow. And so I'm actually going to do part B first. I'm going to find out the rate at which the length of his shadow is changing. Because I know once I have that, I can just add these two rates to get part A. So we said we use a proportion here, similarity. So I know x over 5 is equal to x plus y over 16. So I'm going to go ahead and cross multiply. 16x equals, when I cross multiply here, I have to remember to distribute that 5 to both terms. So I have 5x plus 5y. Collect my x's, and I get 11x equals 5y. So there's my relationship. Now I just need to differentiate. So I'm going to get 11 dx dt equals 5 dy dt. Oh, you know what I just realized? I pulled the wrong number here. Our man is actually 6 feet tall. Sorry about that. Let's go back and correct this quickly. So my man is 6 feet tall, so I need to replace that here, x over 6. So I'll get 16x equals 6x plus 6y. So now I'll get 10x equals 6y. And so 10 dx dt equals 6 dy dt. There, that looks better. Okay, sorry about that. So now, again, we look at what we know and what we're trying to find out. So I need dx dt or dy dt. So I know, again, this man is walking towards the lamppost at a rate of 5 feet per second. Since this distance is decreasing, I know that rate is a negative 5 feet per second, and I'm trying to find out about the rate of change of the shadow. Okay, so now that I know dy dt, I can go ahead and plug that in. That'll allow us to solve for dx dt. So I have 10 dx dt equals 6 times negative 5. So now if I isolate dx dt, I have negative 30 over 10, and I get negative 3 feet per second. So that's the rate at which his shadow is decreasing. So now I want to talk about how fast the tip of that shadow is moving. So again, here's where we know that we have x plus y is equal to z. So now if I differentiate with respect to t, I get dx dt plus dy dt equals dz dt. And so now I know both of these, oops, let's move this over here. I know both of these two rates. dx dt we said was negative 3. dy dt we said was negative 5. So if I add those rates together, dz dt is equal to -8, what do we have here, feet per second. So that means that negative here indicates that the tip of that shadow is getting closer and closer to the lamppost. That distance is decreasing. So that's it for this type of problem. Really quickly, let's go back. I think the only thing really that we need to add on page 8 is the volume of a cone. Which we said is volume is pi over 3 r squared h. So those are all the types of related rates problems, and we'll spend the next few days practicing them all mixed together. Good luck!